Okay, everybody, we're back. Confidence intervals. So, three topics here that we're going to look at. Basically, we're going to look at what is a confidence interval, but also confidence intervals for a population mean when we know the standard deviation, and then we're going to do the usual when we don't know the standard deviation, and then we'll also look at confidence intervals for a population proportion. So, what is confidence interval? Well, statisticians actually prefer to have an interval estimate of a parameter. And what an interval estimate is a range of values which are constructed from sample data used to estimate the parameter. The confidence coefficient, which is 1 minus alpha, measures the probability that the parameter will fall within the specified interval. So what are the intervals we use? Well, we go 99%, 98%, 95%, and 90% confidence intervals, which we sometimes just call CIs. So the confidence coefficient can be thought of as the complement of the significance level alpha. Remember, complement means you go 1 minus alpha to get to the complement. What does a confidence interval actually mean? Great question. Well, confidence intervals are constructed at what we call a confidence level, such as 95%. So what does it mean? Well, it means that if the same population is sampled on numerous occasions and interval estimates are made on each occasion, the resulting intervals would include the true population parameter in 95% of the cases. So basically, we are estimating, say, the mean. So maybe we're estimating the mean of something. And if I say, hey, the 95% confidence interval is, 2 to 2.75. Then what that means is that we're 95% sure that the true mean is in between 2 and 2.75. So it's kind of like giving you a range of values of which we're saying, hey, we're 95% sure that the actual mean is somewhere between these two values. And that's basically, in a nutshell, what a confidence interval is. What is this? The probability that the confidence interval will contain the population mean mu in repeated samples is denoted by 1 minus alpha. So, 1 minus alpha is referred to as the confidence coefficient. 1 minus alpha times 100 is called the confidence level. So the confidence level is the success rate for the method. So what are we going to do now? If we have a population where we know the standard deviation, and if the population is normal or if the sample size is large, as in n is greater than 30, then we are basically going to be using this formula down here. This would be the confidence interval formula. Now, it looks a little funny. So you got x bar, and then this is plus or minus. So what you're going to do is you're going to take x bar and you're going to add to it whatever this factor is. So it looks kind of scary, but if you break it down, it's just z alpha divided by 2 times, so this is multiplication here when there's no symbol, the standard deviation divided by n. So you're going to kind of write some square brackets here. And you're going to write the small number first and then the big number second. So what I mean is you also go x bar minus z alpha divided by 2 times the standard deviation times n, comma, so that'll be the small number, right, because you're subtracting this factor. And then you're going to go x bar plus this special factor here. So basically, you are adding and subtracting whatever this number here ends up being from x bar to get the range. Let's take a look at a question here, figuring out the z alpha values. So if we're doing a 95% confidence interval, then remember you need to find the 1 minus alpha is going to be 95%. Okay, so to get back to 1, alpha has to be 5%, right? So basically, if you're doing a 95% confidence interval, your alpha value is whatever it takes to get you to 100%. Okay, then you need to find alpha divided by 2, because if you look in the formula, it does say to go alpha divided by 2, right? What we're doing is we're taking that 5% error and we're putting it on both sides of the distribution, so we're splitting it in half. So dividing it by 2, you're going to get 0.025. Okay, so we need to find that normal point z at 0.025, and you're looking up the area under the standard curve. go ahead and look it up on your z-score table if you like. You can also use the t-score if you go to infinity. Now, I didn't actually have mine open. Here's my t distribution. So I'm going to go use degrees of freedom infinity. So it's the same as the z tables. So 0.025, and you get 1.96. Where is it? Okay. So this gives negative 1.96 because we're on the left tail, and we know that the right tail would be positive 1.96. Okay. Here's a nifty little chart for you. Now, by no means do you really need to memorize it, but it just has all the confidence intervals that we generally do, so 90, 95, 98, 99. And then the 1 minus alpha, so then figuring out your alpha value. So if you're doing a 90% confidence interval, the alpha value you're looking up is 10% divided by 2, right? So 0.05, and then you're looking up a z 0.05, or you can use your t-table, right? So you would get 1.645. So I actually recommend that you pause the video here, see if you can go find these other alpha values, see if it makes sense. If you're doing a 95%, then your alpha value is 5%, right? Remember, these two have to add up to 100, I think is the easiest way to figure it out. Don't forget to divide it by 2, and we actually just did this one, right? We get 1.96, and try these last two. When you're done, you should get 2.33 and 2.575. Okay. We're on to the next slide. So let's actually go ahead and try out the question. So confidence intervals aren't very big questions, but they're neat little questions. Like, what do we got? Estimating the mean payment time. This is like sort of like a reoccurring example in the textbook, but we got an X bar waiting time of this 18.1077 minutes, 65 samples, and we know the population standard deviation. Then it says find the 99th percentile or the 99th percent confidence interval for mu. So you don't really need to do this, but it can help you remember like that you have to split it in two, right? So you can try a normal distribution and just remind yourself you're breaking up the error into the two tails here, and you got 99% in the middle. So your alpha value is 1%, right? Whatever you got to add to 99 to get to 100. And now our formula needs alpha divided by 2, so we got to look up, 0.005. So 0.005. We can go look it up on the good old t-table. 0.005. There it is, all the way down to degrees of freedom infinity. So 2.575. 2.575. There we go. So now we know that that's the value right there, and we can go ahead and find our 99% confidence interval. Now remember, this is the formula here, right? So it's got that plus or minus. Now we're going to use 0.005 times sigma divided by square root n. Now what I recommend you do is go figure out what this number is. Like just this little piece here, right? Because this is the part of the formula that you're going to add and subtract to x bar. So go figure this out. So we got 2.575 times the standard deviation, which is 4.2, divided by square root of 65. Now go ahead, plug that in on your calculator and see what you get. Go ahead and pause it. Now when I typed it in, I got 1.3414. So this is that basically that plus or minus number that we're going to add to x bar. Okay, so basically we're going to go x bar plus this number, 1.3414, and we're going to go x bar minus that number. Now, I actually just wrote it in the wrong order, okay, in the square brackets, right? We write the smaller number first and then the larger number. So for this one here, x bar minus 1.3414. Okay, so here's x bar, so go 18.1077 and then subtract 1.3414, and you should get 16.8. All right. Now go x bar plus that number, so 18.1077 plus that number, and you get 19.4. So what is this? This is the confidence interval. So this is the confidence interval. It's actually the 99th percent confidence interval. Okay, so we're 99% sure that our true population mean is somewhere between 16.8 minutes and 19.4. Okay, so that's what the confidence interval is telling us. We can do another one. This one here is a 95% confidence interval for mu and compared to the 99th percentile. So same question, same numbers as before. It's just this time we're going to find the 95th percent confidence interval. So for the 95th percent confidence interval, alpha, right? 95 plus what is 100? So it's going to be 5%. So when you go alpha divided by 2, you're looking at 2.5%. So you need to find z at 0.0025. Now you can go look it up. We've done this one before. You get 1.96. Okay. So again, you need to look at this formula, plus or minus z at 0.025 times sigma divided by square root n. And what does that mean? Well, it means you're going to go x bar minus some number and x bar plus some number. Now we can go and actually figure this number out here. We know it's 1.96 times, what was the standard deviation again? 4.2 divided by square root of 65. So I recommend you actually go type that in on your calculator. Now in this case, you get 1.0211. So now we know the number that we are adding and subtracting. All right. Now x bar was 18.1077. So this number subtract our correction factor, it gives us 17.1. And then when you go x bar plus that number, you're going to get 19.1. Okay, so now this is the 95% confidence interval right here. Now, it says, can you compare it to the 99th% confidence interval? Well, this range is 17.1 to 19.1. Now, if you flip back a slide, the 99% confidence interval was 16.8 to 19.4. This is the 99% confidence interval. So if you're comparing them, I suppose that you'll notice that we're only 95% sure for this one that the mean actually lies between these two numbers. Now we're 99% sure the mean lies between these two numbers. What's the difference? Well, you see how we made the range bigger, right? So the top end is 0.3 bigger and the bottom end is 0.3 smaller. It's a coincidence that it happens to be 0.3 both times, just so you know. However, the range is bigger. And because we have a bigger range, we can be more confident that our mean is in that range. So the 99% confidence interval is only slightly larger. But I would say is larger. Is the big thing. Is larger than the 95% confidence interval. Okay? If you're going to be more sure, you got to make that range bigger. Yeah! Makes sense. All right, well, what if we don't know? How do we do a confidence interval if we don't know sigma, if we don't know the standard deviation? Or what if maybe our sample size is small? So if sigma is unknown, which is usually the case, and n is less than 30, we can construct a confidence interval for mu based on the t distribution with n minus 1 degrees of freedom. And lo and behold, it looks like this. So it's exactly the same formula, really. It's x bar plus or minus, but did you guess it? It's going to be T alpha divided by 2 times. Not sigma. We don't know sigma. We're going to be using S. Because we'll be using the sample standard deviation. S divided by square root n. So there's your confidence interval. Don't forget it is degrees of freedom n minus 1, which seems to be par for the course. So let's take a look at this question. Sometimes they can get a little wordy here, but a company's financial health is determined by its debt to equity ratio. ratio that is too high can be an indication of financial instability. A company samples its portfolio of commercial loans 15 times. I believe we've seen this question before. And finds the mean debt to equity ratio to be X bar equals 1.34 with a sample standard deviation of 0.1921. And the bank wishes you to calculate a 95% confidence interval for the loan's mean debt to equity ratio. So they're saying, hey, can you give us a range of what the mean debt to equity ratio actually is? And the answer is, of course we can. So I kind of have it laid out for you on the next slide. So here's the data from the question. X bar is this, standard deviation, and n was 15, right? So they sampled it 15 times. Now we're doing a 95% confidence interval. So, alpha is 5%. Okay, but if you want to do the whole 1 minus alpha, then that's 0.95, right? So alpha is 0.05, alpha divided by 2, just cut it in half. There we go. Now, remember, we're using the t-table. Okay, we're not going to degrees of freedom infinity. Okay, so for n equal 15, degrees of freedom is 15 minus 1, so we're going to go and look at 14, and we're going to find 0.025 and 14 on the t-table. So let's see. 0.025 and go down to 14, or as close as you can get. So 2.145. 2.145. There we go. Now we can construct the confidence interval. Remember, you're using this formula. All right, so probably pays off to go ahead and figure out what this correction factor is going to end up being. So 2.145 times S, which was 0.1921, divided by square root n, which is 15. Be careful that you don't use 14, right? That's just for the tables. And let's see. Well, when you type that in on your calculator, give it a shot, I get 0.1064. So there's the correction factor. Now you're going to go X bar plus and minus that number. So you can just go ahead and write, you could just write this for work. X bar plus or minus 0.1064. That's fine, right? We wrote X bar up here. You have the work of how you found that number over here, very important. And then if you wish, you can just jump straight to the answer here. So I got 1.2369, comma, 1.4497. Now, well, that's it. I was going to say write the smaller number first and then the bigger number. And you're rocking and rolling. Okay, there is a question where sometimes we just ask for the sample size determination. So if you know sigma, you can find the sample size n. So this is just sort of a strange backwards formula. Sometimes it's handy. So it's generally used to sort of figure out how big of a sample size you're going to need to get a particular confidence interval. This is so that X bar is within E, which is called the margin of error, units of mu with 100 times 1 minus alpha percent confidence. So E will be given. You won't have to figure that out. Let's try one. We got the same formula, but for t-table. So if we don't know sigma, we're going to use just the sample size, we're just going to use the standard deviation from the sample. Then same formula, just using the t-table, times S divided by E squared. And yeah, that's going to make it so that X bar is within E units of the actual mean. With whatever confidence interval we're actually looking at. So the number of degrees of freedom for T alpha divided by 2 is still n minus 1 degrees of freedom. Now, all these formulas are on your formula sheet, by the way, so don't need to worry about that. So let's look at a quick question. These aren't crazy questions because you're always going to be getting E. So it's just sort of recognizing that I'm asking you what would the sample size need to be so that we can get this confidence interval that we're looking for. Remember, it's the minimum sample size. So it just gives the researchers basically, or companies, whatever you like, an ability to know approximately how much data they need to gather. Okay, so it can be sort of a cost-saving thing. So the candy company wishes to find the sample size that is needed to make the margin of error in a 95% confidence interval from you equal to 8. Okay, so it's talking about the margin of error, so E is 8. What else do we need to know? Well, 95% confidence interval, so your alpha value is 5%. So when you go alpha divided by 2, you get 2.5%. So we're going to be looking for Z 0.025. Okay, so assuming that sigma is known and it's equal to 40, and using this value here, which we can look up on the tables at 1.96, go ahead and figure out what the sample size n needs to be. So this is the formula. Divided by E and it's squared. Well, we know that this Z value here is 1.96 times, now what's sigma? Well, it said sigma is known to be equal to 40, so plug in 40 divided by E, which is 8, and then you're going to square it. So don't forget order of operations here. Okay, so 1.96 times 40, divide that by 8, take whatever that number is and square it. What do you get? Go ahead, try it out. Pause the video. Well, if you do, you get 96.04. Now, just remember, this is the minimum sample size. So if you need 96.04, you might be tempted to round down, but actually need to round up. Okay, so you're going to round up to 97. Okay, because you need at least this much data, so you need at least 97. So rounding up, got to sample 97. Okay, now I have a very similar question, but for using the t-table. Sample size requirements for 95% confidence interval, but we don't know sigma. So go ahead. This is the sample standard deviation that we're going to use right here. We're, still 95% confidence interval, so when you go t alpha divided by 2, you're looking at t of 0.025, which I do believe, what's degrees of freedom? Remember, degrees of freedom is going to be 5 minus 1, okay? So degrees of freedom is 5 minus 1. Remember, it's alpha minus 1 for this, right? So we can go look it up. 0.025 for 2.776. There we have it. So you are using this formula here, and I will pause, or I should say you should pause the video. I can't pause your video, that's crazy. Using that formula there. Okay, pop in the numbers, see what you get. Pause the video. So you should get 99.21 or 100 when you round up. So there's that question. Now, there's a couple slides we're going to skip here. Not this one, actually. We're going to do this one. So last thing, I know I said we weren't going to do it, but here we are. Just to make sure that we do cover it. For a population proportion, here's the formula for confidence interval. Now, same exact idea as the Z-score and the T-score tables, right? Except that you got p-hat. And just remember, p-hat is going to be x divided by n. Okay, so whatever number of you survey 60 people and 20 say they're going to buy your ice cream. Okay, so it'd be 20 out of 60, and that's p-hat. And then you got to calculate these other numbers, p-hat times 1 minus p-hat. Okay, right, so I even have it down here. We'll recall that p-hat is calculated as x divided by n, or, number of successes divided by number of people, number of samples, whatever it is. Every question's a little bit different. n should be considered large if both these two things are true. So it's just like when we're doing the binomial distribution. N times p hat should be greater than or equal to 5, and n times 1 minus p hat should be greater than or equal to 5. Now, what I got here is, I do believe, yes, I have a question that involves using the proportion one. So I will quickly go through it right here. So the company, estimating the prevalence of a common drug side effect. So the company wishes to estimate P, the proportion of all patients who would experience nausea as a side effect when being treated with Thymosin. If 35 out of 200 tested experienced nausea, basically find the 95% confidence interval. I know it doesn't quite say, but it wants to know a 95% confidence interval. So we know the alpha value is 5. And we can go calculate Z alpha divided by 2, so Z at 0.025. We've done this one a few times now, it's 1.96. Let's go find P hat. So P hat is going to be 35 out of the 200, and N is 200. And 35 out of the 200 is 0.175. Yeah. Make sure you check. So check. So we can use this formula if n times p hat is greater than or equal to 5. So 200 times 0.175. Well, that's 35, right? We're working backwards here. So yeah, that one works. And then we need to check that n times 1 minus p hat is greater than or equal to 5. Well, the good news is that 1 minus 1.175 is going to be 0.825, right? And that's equal to 165. So that's good too. So that's all good. Well, now we can do the 95% confidence interval using, this formula here. So p hat plus or minus Z alpha divided by 2 times. Now it's the square root of all this stuff. P hat, I love that. P hat 1 minus p hat divided by n. So it'd probably pay off to figure out what this whole number is here. Got 1.96 for the Z value times square root. See if we can squeeze it in here. So p hat times 1 minus p hat, which is 0.825, divided by 200. So go ahead, type it in on your calculator. So multiply the two top numbers, divide by 200, do the square root, then multiply that by 1.96. When you do it, you will get 0.053. Ladies and gentlemen, what a beautiful number. Plus or minus, right? Part of the formula. So you're going to go p hat plus or minus 0.053. P hat is this number here. So go ahead, take that number and subtract it for the first one. You're going to get 0.122. And then p hat, 1.75, plus this number, 0.053. You get 0.228. There we go. So we are 95% sure. It's a 95% confidence interval. We are 95% sure that the true proportion of people who experience nausea as a side effect when using this Thymosin is somewhere between 12.2% and 22.8%. So there you have it. This is what they tested, right? And we are 95% sure that it's actually between 12 and 22%. So that's it. This slide here might be in your notes. You can skip it. We're just too many sample size things. We're not going to do it. We did the most basic ones for Z and T, so we can skip that one. And this is also the question you can skip because it's the example for this thing here. So there you have it. Those are the notes for this week. Try the homeworks, and you know what? I have a feeling that we'll see you again. Bye-bye.